Alright, so a metric space is called separable if it contains a countable dense subset. So we want to show that our favorite metric space, at least in this textbook, RK, is separable. And the hint, so this type of exercise is like, normally to prove that something's separable, you have to exhibit a countable dense subset, so that can be difficult, so they actually tell you which one to use. And it's just set of points which have only rational coordinates, so that's QK. So we want to prove that QK is a countable dense subset of RK. So QK is a direct product of finitely many countable sets, because Q is countable and we're taking the direct product of K copies of Q. Okay, so there's finitely many direct product of finitely many countable. So is a direct product of finitely many countable sets, and thus is countable. Okay, so countable down. Now we need dense. Oh, certainly, it's a subset. So for density, let U be an open neighborhood of RK. We need to prove that there is some QK, some element of QK in this open neighborhood U. Alright, U contains, so this could just be an open set or open subset of RK. U contains an open ball, call it B, so this is going to be a ball with some radius and some center. We don't really care what the radius and center are for this problem, so we don't really need that, but whatever. B then contains an open rectangle. We're going to call it R, and here we need to specify what it looks like. So it's going to be the direct product from I equals 1 to K of, so the intervals are going to look like AI, BI, and of course each AI is strictly less than BI, and this rectangle is going to be contained in B. And of course this is possible because what you could do is you could take the X, and then there is some delta based on R, such that if you consider a rectangle such that for each coordinate you go to the left and right by at most delta, then the resulting rectangle will be in the ball. I think delta needs to be less than the square root of K times R or something like that? I don't know. I talk about it a little bit in Spivak's textbook, because in Spivak they define open neighborhoods to be rectangles rather than open balls. And so there are some cases in that textbook where you have to go between the two, and there's a lot of estimates where you have to, you can find this rectangle. I just don't want to go through the details. Now, so for all I, there exists some Ci, which is a rational number, but also in this open interval from AI to BI. That's because the rationals are dense in R. Then C, which we define to be the points C1 through CK, well, this is going to be an element of QK because each entry is in Q, but each CI is in the interval from AI to BI, and so it's going to be in R as well. So it's in the intersection of R and QK, and R is the subset of U, so this is contained in QK and U. So what that means is that any neighborhood or any open set in Rn, any open set in Rk contains a point in Qk. So thus, QK is, well, thus QK is a dense set, and hence QK is a countable dense subset of RK, which implies that RK is separable. And it turns out that separability is a really nice property for topological spaces. We'll talk about this more in future exercises, but it's nice to know that this metric space that we work in a lot, specifically RK, is in fact separable. And that's one of the reasons that we work in it, actually, is that things work out really nicely in RK. But anyways, that's all there is to this exercise, and so we're done.